So I'll post this as soon as possible. Right. So far, we know the equation, the standard equation of forces is F equals ma. We talk about forces, right? The friction and the gravity and the friction, and so many things about force. And then acceleration, of course. The change of velocity is the acceleration, and we were talking about angular acceleration as well as the other ones as well. Okay, so now change in mass is also an interesting topic, right? So why we picking rocket motion? What is it has to do with mass?
When the fuel burns, it loses mass.
Yeah. So when you're sending a rocket up, right? You may have seen rocket is have some fuel tanks like this. They start burning, and so it's burning very fast. Because of that, there's a force built by a thrust, right? The thrust. We're going to talk about thrust today. And since there is a thrust this way, it will push us the object upward. That's how it's going up, right? And it's going up for some sort of distance. This tank will be empty by burning out. So then you don't need this tank anymore. Because of that, after some distance, you drop that off. So you will have these going down, right? And like that, only thing that you have to do is somehow go this out of the atmosphere. As soon as it's reached this place, uh, you don't have to worry about much because of the gravity is out of the area, right? In that case, you need this whatever you pushing it up until you reach the atmosphere. This is the Earth. So the area of gravity, if you go beyond that, that's all cool, right? So anyway, so that's why you dropping this to reduce the mass as much as you can. So so this equation. So what we're going to look at here is changing of mass, right? So that is the this model is all about, right? So let's move on. Right. So the thrust is the definition here. Is a mechanical force caused by the acceleration of a mass of fluid, actually, in the opposite direction. So what this means is, if you imagine this uh, mechanical force caused by acceleration of mass of fluid in the opposite direction. So the flow of fluid as downward, and because of this, it will thrust upward, right? You know what this means, right? So you have done fireworks. It's the same case, right? When you burn the fireworks, it's going up, and that has the same effect, right? So the rockets and the fireworks, same thing. So anyway, so right. Okay, so how do I put that into an equation? So this is what the image look like. So the gravitational force pull you down, right? And of course, there's air drag, which is the air influence on this object, also causing the force downward because it's moving upward, right? So there are two forces working against you while you're going up. Okay, so that is one thing that you have to consider. And the other is the give the equation for the thrust is a change in mass over time. So you can look at this. Now in this case, what we're talking about is changing mass. So this is what delta m over delta t for a little time of seconds or milliseconds, whatever the time, there's a change of mass, right? So this is actually directly proportional to your thrust, right? And so the c is the velocity of the gas relative to the rocket. Actually, it is just a constant value for a given time, given thing, given system. So that's why it's considered as c, but can change. So t is equal to c, little change on this over little change of this, mass over time. So that's what the equation gives you. Okay, and yeah, so pretty much this is the equation for the trust. So trust is not the only thing that you have to consider in this case. There are a little bit more factors that we have to look into. So here, let's we talk about only the trust, right? Uh, with up being positive, so that means going upward is the positive direction. Suppose the rocket traveling up on the speed of 500 meters per second. This is speed, the velocity, right? And the speed of downward gas is 800 uh, meters per second. So give the c value. Obviously, it is going on this speed upward, and if 800 is the downward by the gas, so then the c value is just the difference of these two values. Okay, this is always the case. So in that case, you may see the c is changing. It is not really a constant at all the time, but depending on the speed here. But at the given value, it is constant. So the trust is depending on whatever the given moment or the time constant value over t. Maybe this is if you are maintaining a one speed on the rocket, for that moment, the c will be constant. But if it is on acceleration mode, yes, the c is changing, right? Okay, so that is one thing that you have to keep in mind. Even I call the c is a constant for the whole thing. No, this is not the case. It is on the for the given speed. This is the constant. Okay. Suppose over a period of 0.1, 2 kilograms of the fuel burns. Right. Give the engine thrust. In that case, well, that is a change of mass within a given time, right? So it is a very little time. So okay, so let me come back to this whole thing again. The thrust is equal to c change of mass over change of time. In this first problem here, we find what is c, right? How we calculate the c? Well, it says it's the rocket is traveling upward, the given speed of 500 meters per second, and then the downward gas, the downward is 800 meters per second. So this is how much downward gas means. So the speed of gas means when it burns, how much it will get out from the system. So the difference between these two we consider as the c value, right? Since upward is positive, we will have a negative 300 as the difference between these two. Okay? And then suppose the period of time, so it is giving an interval, delta t is equal to b 0.1. And then the amount of mass, which means after burning the fuel. So if you have a tank of this with a kilogram amount, and it will burn 200 of 2 kilograms of this within a given second. So that means the change of mass will be what? Delta m is going to be 200 kilograms, right? So you may see the actually units are okay. So it is we're talking about seconds, meters, and seconds and kilograms. So it's all matched together. So in that case, we don't have to worry about changing any of it. So this is right here. We come up with the value minus 300 multiplied by 2 divided by 0.1, right? Okay, so this one is 600, obviously, on the top, right? Divided by this means you can write it like this if you want, right? So this is equal to reciprocal of that, which is 600 multiplied by 10. So units here is ms, and uh, this one also have a ms, right? And then and kg, right? So, and then there's another s here, which divided by this. So it is kg m s squared, which is equal to what? Newtons. Okay, so that is how you get the newtons. Newtons. That is the answer. Okay. Right. So yes, obviously, it is a good way of testing your answer is correct to see what are these. Did you get the right values there? So if you didn't get the s squared here, obviously there's something wrong. So, but we get s squared by changing this value, and then also c has s in it. So that's what s squared is. Okay. So like that, so you can calculate this. So these are the the most simple calculations that you can do using this equation. Okay. All right. So then there's another thing which is called impulse. So now the thrust here. Uh, so actually, you have to accelerate when you're going up, right? So there has to be acceleration somehow. So because of this, um, we consider change in uh, thrust. Like for example, whenever it's going up, it's reduced its mass to something as it's going up. So that means whenever the mass is less, if the force is a constant, and if the mass is going down, in order to keep this force constant, you have to have increment on A, right? So the balance of these two will keep intact this value. If this value, to keep this value constant, what happens is if the mass goes down, acceleration goes up, right? So then the multiplication will be the same, right? What I'm saying here is if this is 6 and if this is 3, and we need 2 here, right? Okay, so this is this, this is this. But if I have this one drop to 2, to get this 6, obviously you have to increase this value to 3, right? So like that, acceleration always going up in order to keep the force constant. Okay. So in this case, that is called impulse. So it's a change of velocity, change of speeds. That means acceleration happens, right? And then the acceleration also going up. So this is I equal delta t. So that is the impulse which is happening on the object when you want to do these things. Whenever it changes the acceleration, there's something called impulse. That means it's pushing up, right? Pushing up the object. So that's the impulse is a product of the thrust and the length of time. So the thrust and the length of time, when using those two factors together, we call impulse. And also there's another one called specific impulse. I will show you that in a minute. That is a per unit of weight. You can calculate that by per unit of weight means you have to divide by m something, the weight. And that is also, we're going to discuss that ISP, right? But for now, this is what you know, which is an impulse, is the thrust multiplied by the time. Okay, so now there's another equation. So we have two equations now we know about moving objects. So there it is. The specific impulse means I'm just measuring the change of impulse over the weight that you carry on. So that equation, if I write it right, now I said impulse equals change of thrust multiplied by time, or the thrust multiplied by change of time. Let's write it like that. Thrust multiplied by change of time. How long it goes is whatever the time it goes, the I is equal to that. Okay, and then the specific impulse means as P is how much change of weight in this case, right? The weight again, when you're measuring a weight, the units will be kilograms multiply by the gravity, actually, right? The acceleration. So in this case, it will be the change in mass over gravity, which is G, right? And this one already I know. This is the equation for this. I can write that here. So the specific impulse that I can get from ISP is equal to T is over G, right? So that is something. So now the funny thing is, I already know one equation for the thrust, which is what? We already know one equation, which is a T equals what? What we had up there? Anyone can remember? What is T equals to? Right here. Change of M over change of T, right? Change of M over change of T. So that's the one equation. This is equal to C times change of M over change of T, right? So this is one equation. Yeah, so when I take T out on this one, T also equal to what? Leave the T there, then multiply everything by mg. So it is ISP, right? And so this is going up. So that is what? Change in weight, right? Mg. And then if you come this one down, is delta T. What does that mean? That is also what? Change in weight over time. Change in weight over time multiplied by specific impulse will give you T2, right? So this one is a constant value. So I don't want to put it there. I can write it like I, S, P, G. And then this is changing M over changing T, right? So in other words, I can write this ISP multiplied by G, Tm over Tt. That is also thrust, right? So there are two equations to calculate the thrust, right? That implies one more thing, which is I can say when I take the first equation, which is this one right here, right? If I take this one, I know this is C Gm over dt, right? Is equal to what? ISP ISP into G into Tm over dt, right? Yeah. So what can I say about this? It has the same values. This one, right? So you can see the C is equal to specific impulse multiplied by gravity. That's also another equation, right? Right. So yeah, so those are the connections that we can consider. Then also another one, which is actually thrust is a force, right? When the thrust is a force on the object, that means what? It is also must be equal to ma. So this is a force actually, right? So in this case, I know that T is equal to ma, which is the force thrust. And T I can write as specific impulse multiplied by G multiplied by change in M over change in T, which is equal to this, right? So then by this, I can also calculate what is acceleration. Acceleration also equal to ISP G Tm over T by M. Right, so I just write tons of equations now, right? That is only, but what you learn is three equations. One is the thrust is equal to C delta M over delta T. That is one equation. Second equation I learn is the specific thrust, which is ISP. Well, let me see. I I is equal to what? Right up there. Right. What is I is equal to? Change in trust over time. Right. So that's the second equation. Change in um, change in trust over time. Right. I'm sorry. T change in time. Right. Clear this out. That's the second equation. The third equation is what? Well, I can say specific impulse, which is SP is equal to I divided by change of weight, right? This is also I called T over delta T divided by um, delta M and G, right? So you can see this part right here is the same thing, this part right here, the other way of this part right here, delta T, right? The opposite of that, okay. And then the fourth one, which is right here. I'm just putting up everything up and down and move around. So then I can write same thing. This T, which is, let me write it like this, so it will be easy for you to identify. This one and this one is the same, right? Okay, so that is the fifth one. And the sixth one I came up, the fifth one I came up with. Since T is equal ma, we include the acceleration here. And then T, I can write this form right here. So this is the ISP G delta M over delta T is also equal ma, right? Out of this sixth equation, I can get A is equal to ISP T delta M over dt. So I had to move this M this way. So this is whole thing divided by M. So 6 equations. Well, it's not that hard for you to remember. You don't have to remember, means you don't have to memorize. It's already giving you. But these are the equations in NASA. Mostly people use, right? Why? Because they are the ones who are talking about rockets and stuff. And also the SpaceX. So if you really like to go on those areas of studies, you may be familiar with these things, okay? Trust and the movement of rocket with the weight changes over time and how that behaves. Okay, so those are the equations I had to give you on this case. And then some problems here, right? So then let's talk about this. But the full burning in 2 seconds in parts, the thrust is 75 to a rocket, find the impulse. So it's easy, right? So this one is very easy question. What I know so far is I know I is equal to thrust multiplied by change in time. Change in time is 2, right? And the thrust is 75. So 75 multiplied by 2 give you the impulse. So the impulse is 150 newtons per second. Where is this Newton comes in? Well, my T is Newton, right? That is a force. Actually. So that's easy to find. And then there's another one. It's suppose the kilogram, 0.5 kilogram of the fuel of part above burns in 2 seconds. Find the specific impulse. So I know SP is equal to I divided by change in weight, right? So in this case, it says, all right, so now it's burning in some sort of value. Change in weight is the fuel which is burnt within 2 seconds is this much. So it changes its weight 0.5 kilogram. And of course, I have to use weight here. That means I have to multiply this by G. So I get whatever the 150 up there. That's my thrust. Divide that by change in weight, which is 0.5 multiplied by 9.81. Whatever you get, the answer here is 30.6. Like that. Okay. So those are the problems that you can solve. Okay, so it's pretty very short lecture actually. How you deal with these things, and this is how you draw it on the graph, and then you can see change in mass, initial mass is there, rocket mass is there, the burnout time is there. Usually when you go up and up, rocket mass also changes. That means you drop pieces down, right? Whenever you're going up, if it's burned down, if the tank is empty, you can drop it. So then your mass is going less. So the initial mass and all that will be your total change in mass influenced by all three of these. That's the change in mass. Okay, and then change in mass and the acceleration due to gravity is a constant value, and the specific impulse we know how to calculate. So all this causes to the acceleration. So that's why we have this equation emphasize only the acceleration. So the acceleration is as one value depending on the change of mass over time multiplied by the gravity multiplied by a specific impulse divided by m, right? So that total thing is acceleration. So the acceleration in case of writing in terms of velocity is a change in velocity. So then that costs each time what is the velocity. So the velocity is what? Actually change in position over time. So change in position over time is the velocity. So in that case, you can write this. So in exactly you can find the position of the rocket by calculating on this. Okay, so this is what the diagram is. So I like you to study these diagrams very carefully. The reason for that is whenever you're writing your own one for your project, you should be able to understand the parameters you are applying and using these equations right here, right? How are you really going to manage your diagram? That is a part of your learning. I'm not going to spoon feed you and give you everything that you should learn little by little. I like everybody put some effort to do by yourself. If you have questions, you can ask, of course. I'm here to help you out. But these things is very important that you do by yourself, right? Okay, so there's a little, as I said, I can just point to the moon. By reaching the moon is up to you, right? It's always the case in this case as well. I'd like you to do some stuff and learn how to play with it and get some good output results like this. So let's analyze this. So now this one is time in seconds, right? And you can see starting from 0 and it's going on this. And then the model diagram for the rocket motion. What is this showing here? This is a position by meters, right? And this is the time of the rocket by the velocity and the position. So this is the position changes. Okay. That's the position changes. Why is it minus 1,000? Not sure why they're putting minus 1,000, but that's not the position. That is actually the we consider the velocity is actually but this black one is the velocity here, right? So it increases and then the decreases this, but position is always going and change. So this is where the rocket is reaching the atmosphere and then it will slow it down. Because why is it slowing down? Does anybody know why is it slowing down? Can anybody tell me why when the rocket goes up and suddenly slow it down like that? Anyone have any idea why the rocket slowed down? You can see it's dropping its velocity very fast. Why?
Does that have to do with the drag?
Drag has to do a lot of things here. There's another thing matters in this case.
The fuel burns and the mass goes down, and then the thrust goes up, and then gravity pulls it down.
Well, if the mass goes down, it has to go fast, right? Like I said, if we're using the same, see, this is the rocket, and there are two things against moving up. One is a drag of the air. The other is the gravity. Those are the two forces work against you, and then he's going up, right? So the difference between these forces will be F minus drag force and minus gravity, right? So this is equal to ma, what is the acceleration, right? If this goes down, this goes up. So that means actually to keep a balance on this, what this means is your acceleration is up means your velocity is going up. But in this case, velocity drops after a certain time. So my question is why the velocity is dropping in this case?
It burned all its fuel and now it's being pulled down because there's no thrust.
Yeah, there's no thrust, right? Because you don't have any more fuel in it. Why? You burn down all the fuel when you're going up, right? So the thrust will drop down, right? So because of that, it slow down.